All right, today and next lecture, we'll be talking about continental rifts and rifted margins, which are extremely interesting and important, and we have a lot of slides to get through, so let's get going. All right, so what we're seeing and what we'll talk about is the sort of rupture of a continent to form a rift that matures and then continues to expand. As the lithosphere thins, the asthenosphere rises, and we begin to get a new ocean. And then the next thing you know, you turn around and there's the Atlantic Ocean. So that's kind of what we'll be talking about in these two lectures. So let's watch a video. Hi, I'm Bob Stern, a professor of geosciences at the University of Texas at Dallas, and I'm here to explain the Wilson cycle, one of the key concepts of our science. I'll tell you a little about where the idea came from, and then I'll explain the 5 stages of the Wilson cycle. The Wilson cycle describes the sequence of geological processes involved in the formation, evolution, and eventual closure of ocean basins over hundreds of millions of years. Named after the Canadian geophysicist J. Tuzo Wilson, the cycle illustrates how tectonic plate movements cause continents to break apart, form new oceans, and then converge again, leading to mountain building. In 1966, before the theory of plate tectonics was developed, Wilson noticed that the early Paleozoic fossils in eastern North America and Europe were similar, suggesting that these regions were next to each other at that time. They must have been separated by continental drift and formation of an intervening ocean, but this episode of ocean opening must have happened before the present Atlantic Ocean existed. Wilson concluded that there must have been an earlier ocean that opened and closed. Wilson's study supported the still controversial hypothesis of continental drift, which led to development of plate tectonics, which revolutionized the earth sciences. The fossil Paleozoic ocean was named Iapetus. The name Iapetus Ocean for the Paleozoic precursor to the Atlantic Ocean originates from Greek mythology. Iapetus was the father of Atlas, after whom the present-day Atlantic Ocean is named. Naming the ancient ocean Iapetus indicated that this early ocean existed before the present Atlantic Ocean began to form. Here's a simple diagram showing the 5 Wilson cycle stages, which proceed in a clockwise direction and take hundreds of millions of years. The 5 stages, beginning with continental rifting, continue through opening of an ocean and development of passive continental margins. Next is the formation of a new subduction zone. Subduction closes the ocean, bringing the separated continents back together, ending in continental collision. The Wilson cycle starts again. Let's take each of the 5 steps separately and illustrate each with a video. First is continental rifting. As the crust is stretched beneath the rift, volcanic activity can occur, creating faults and eventually leading to the development of a rift valley and a narrow ocean. The animation on the right shows an ongoing example of this stage, the opening of the Red Sea between northeast Africa and Arabia. As the rift widens, seafloor spreading starts in the new ocean, and the 2 continental fragments move farther and farther apart. The margins of each continent subside beneath sea level, making continental shelves where thick sequences of sedimentary rocks are deposited. The animation on the right shows an ongoing example of this stage, the widening of the Atlantic Ocean. At some point, a new subduction zone will form because the oceanic plate becomes too dense and starts to sink. We didn't have any idea about how this happened until recently, because the subduction initiation process occurs rarely, and when it does, it happens on the seafloor, hidden from view. The animation on the right shows how we think it happens. Once the new subduction zone forms, the oceanic plate is progressively subducted and the ocean begins to narrow, and the 2 continental fragments begin to move towards each other. The animation on the right shows how a subduction zone operates. Subduction will continue until all of the oceanic plate is consumed and the continents meet. Continental crust is less dense than oceanic crust, and the subduction zone becomes jammed, leading to the final stage. The final stage of the Wilson cycle occurs when the continents finally collide to form a large mountain range. A good example of this is the modern Himalayas, where the Indian plate continues to collide with the Eurasian plate, closing an ancient ocean basin known as the Tethys Ocean. The animation on the right shows this collision. These 5 stages of the Wilson cycle highlight the dynamic nature of Earth's surface, driven by plate tectonics and the continuous opening and closing of ocean basins. Over geological time, this process contributes to the recycling of the Earth's crust and the constant reshaping of continents and oceans. Thanks for listening. Many sedimentary basins form by rifting, but not all of them. So I asked ChatGPT, what is a sedimentary basin? It responded, a sedimentary basin is a low-lying region on the Earth's surface that has been filled with layers of sedimentary rock over time. It is formed by the gradual accumulation and deposition of sediments such as sand, mud, limestone, and organic material. Sedimentary basins vary in size and shape, ranging from small depressions to large-scale features that span hundreds or even thousands of kilometers. Over time, the weight of the overlying sediment compacts the lower layers, causing them to lithify into solid rock. Sedimentary basins can be found on both land and beneath the oceans and are important sources of natural resources, especially including oil, gas, and some minerals. So here's a map showing the sedimentary basins of the world. This is, global sedimentary basin thickness, 0 to 22 kilometers. And you can see the big ones. There's the Gulf of Mexico, Eastern Mediterranean, Black Sea, Caspian Sea, Bay of Bengal. Those are the big ones. But you notice that there's significant sediment accumulations on them, all of the margins. These are the passive margins, which we'll be talking about later. All right, so there's 5 main types of sedimentary basins, and these are subdivided based on subsidence mechanisms, what causes them to create space for sediments to accumulate, which is called accommodation space. So rifts and passive continental margins are formed as a result of rifting and lithospheric cooling, as we will talk about later. Foreland basins are caused by orogenic loading, which will not be discussed in this lecture, but will be discussed in a later lecture. Forearc basins are related to subduction. They're not very important, but we will touch on them when we talk about subduction. Strike-slip basins, these are small basins with various mechanisms, and we'll talk about them when we talk about transform faults and strike-slip faults. And then there are cratonic basins, and these have an unknown mechanism, quite interesting. But in this lecture, we're going to just talk about rifts and passive margins and the basins associated with them. So the deepest sedimentary basins contain more than 15 kilometers of sedimentary rocks, and they are found in the southern Caspian Sea and the western Gulf of Mexico, basically offshore Texas. I would add the Bay of Bengal off of eastern India and Bangladesh as another. These are generally beneath rifted continental margins. So let's talk about continental rifts, because there's a relationship between these thick piles of sediments and continental rifts. So continental rifts are regions where the lithosphere is being extended. They are as we've gone over a couple of times, they are the initial stages of continental breakup, which sometimes, not always, leads to the formation of new oceans. And here you can see some selected continental rifts, and we'll talk about some of them in this lecture. So here's basically what's happening in a nutshell. So at the top, we've got early rifting. Something is stretching the lithosphere. The lithosphere responds by thinning, and that allows the asthenosphere to rise. And as the asthenosphere rises, it melts. And as it melts, it basically forms magma, which erupts at
what becomes a new mid-ocean ridge, and we create a new oceanic crust and therefore a new ocean. So if we do get rifting leading to seafloor spreading, the rifted crust will begin to subside beneath sea level. That's this stuff basically here is getting thinner and thinner, and it's subsiding, right? And the passive margins will form on both sides of the new ocean. So these are going to be passive continental margins. All right, let's just clarify a little potential confusion of what is a passive as opposed to an active continental margin. So active margins are plate boundaries. Passive margins are not. Passive margins are boundaries between continental lithosphere and oceanic lithosphere, and they are on the same plate with both. And basically where those two kinds of lithosphere join, where those two kinds of crust join. Passive margins mark one half of an ancient rift that opened to form a new ocean basin. Passive margins formed at a plate boundary, but are now situated in a plate interior because of the addition of new oceanic crust as the ocean widened. Passive margins accumulate thick sediments because they are adjacent to continents. The way that sediment is created is certainly by biology. Reefs can do that. They need to be in shallow water, in warm water. But by and large, sediment is derived from the erosion of continents, and that is deposited very close to the continental margin. So let me know if there's any questions about any of this. It's a lot. All right, so here's a kind of sketch of what's happening between unstretched continental crust. Okay, here's 45 kilometers. Maybe this is Dallas. Dallas could be here. And then here we have normal oceanic crust. That could be the Gulf of Mexico. And say between Dallas and the Gulf of Mexico, you've got this kind of transitional crust, which is very interesting. And then two sedimentary sequences. One that's related to rifting, the rift facies sediments and volcanics. And the other are these sediments deposited later during the thermal subsidence phase, which we'll talk about more. All right, here's a good example of a passive continental margin. So UTD's here. This is on the Craton. There's the Ouachita Mountains, Florida. There's Mexico down here. And here is the Gulf of Mexico. And this is the continental shelf. Houston is right there, right? And this is basically just topography and a bathymetric map across a continental margin onto the deep ocean. All right, so all passive margins begin as continental rifts. So passive margins, they're starting to form here, right? There's sediment accumulating in those things, and more here and more here, right? And it's going to change. This could be a lake or fresh water. There's going to be lavas in maybe mixed in here. And over here, you're going to be in the marine environment. So the nature of those sediments is going to evolve as the ocean widens and as the passive margin ages. So there's going to be a wide range of sedimentary environments in these thick accumulations of sediments. At the beginning, you might see something like this. So this is a continental rift where there's no through-going river as opposed to this one, right? So this could be something like the Basin and Range where there's lots of these playa lakes, ephemeral lakes or even salt lakes. Maybe the Salt Lake, the Great Salt Lake, the United States would be a good example. And you get uplands which are depositing clastic sediments mixing with this stuff. And then in slightly wetter environments, you'll get a through-growing river. Like this could be the Rio Grande, right? We'll see this again in East Africa, where the Eastern Rift is more like this, and the Western Rift is more like this. And then with time, as substance continues, the ocean will invade, and you begin to get a sedimentary basin, which is accumulating a lot of marine sediments, some of them clastic, derived from flanking highlands, others biogenic, reefs, and those sorts of things. And these kinds of more complicated environments. And we'll see this at the end if we get there at the end of Wednesday's lecture. We'll see an example of one of these rifts that's progressed through these stages. All right, so there's two different styles of rifts, narrow and wide. So these reflect the strength of the lithosphere. Where the lithosphere is cold, thick, and strong, we have narrow rifts, and a good example of those would be the Baikal Rift up here in Siberia, the East African Rift here along the east side of Africa, and the Rheingraben. The Rhine, we could call it the Central European rift system that goes through here. The Rhine River flows down. Where the lithosphere is hot, weak, and thin, you have broad rifts. And good example of those are the Basin and Range. That's a very wide rift. And another one is in the Aegean Sea between Greece and Turkey. Both of these types can be associated with rift-related volcanism. So, what are the rheological controls on rifting? We talked quite a bit about rheology, and now we're going to use some of that. We talked about these strength envelopes, right? Where the upper strength is controlled by Byerlee's law, the brittle failure of rocks, and at depth where the strength is controlled by the creep of the weakest minerals in the continental crust. That's thought to be quartz. So we can look at different thermal environments, one of which is quite strong and one of which is much weaker. And so here's an example right here in this reference point. We have this strength profile, but right underneath the rift, we have this strength profile. So as a result, because of this is the weakest spot, all of the extension, all of the pulling that's is going to be concentrated in this region. All right. So here we can see the strength profile beneath an evolving rift. Right, there's the thinning lithosphere with the upwelling asthenosphere. This magmas are coming up here. They're going to heat it. The lithosphere is going to weaken it further. And then up here is the realm of brittle failure and the faulting associated with these kinds of fault grabens. You know, these are the features we were looking at with lakes and rivers flowing down them. All right, so if we look at the strength profiles for the three kinds of examples of lithospheric profiles, going from very strong, relatively strong, to relatively weak, narrow rift, wide rift, core complex, which we haven't talked about much, but we will. Here we're looking at different temperature profiles. This is a colder one, 12 degrees per kilometer. This is a hotter one, 30 degrees per kilometer. So at a depth of 10 kilometers, here you would be at 300 degrees. At a depth of 10 kilometers here, it'd be 120 degrees. Much stronger, much weaker. We see that the temperature profiles here in these first diagrams, we see the yield strength for these three profiles here. This one has a lot more area under the curve than this one, and this one has more than that one. And we don't really need to worry too much about the viscosity, but it's these yield strengths that is controlling the width of the rift. So in a nutshell, wide rifts occur in areas of very high heat flow, which is very weak crust and lithosphere. And a good example of that is the Basin and Range. It's a broad zone of very hot and weak continental crust. Now let's talk about a narrow rift. Here we have the East African Rift. It's a narrow rift. You can see there's the Eastern Rift coming down there through Kenya, Western Rift here between Congo and Uganda. And here we see a number of profiles. Here's the Karunganga Basin. Here's the, that I think is down there. The Albert Basin, which is up here. Manyara Basin is here, and the Chubar Basin is here. So these are a number of profiles showing, where the volcanic rocks are and the late Cenozoic sedimentary fill. So this rift is, yes.
I guess I'm just a little surprised. I would have thought East Africa would be a hot basin with Kilimanjaro and all the volcanoes up in Ethiopia and all those other volcanoes in the area.
Well, yes, those are different things. So Kilimanjaro's down here, and it is definitely indicating that there's thermal activity beneath. The Ethiopian rift has progressed to the point of seafloor spreading, right? We've got seafloor spreading in the southern Red Sea and in the Gulf of Aden, and on land here in what's called the Danakil Depression. So that is much broader. It's actually gone to seafloor spreading, but the rest of it is quite narrow. And the lithosphere there is relatively strong compared to the Basin and Range. And
okay.
All right, so East Africa from space, you can see vegetation, you can see deserts, you can see lakes. This is the Western Rift. These lakes define the Western Rift. Eastern Rift's a little harder to see, but it's coming up through here. And then up into Ethiopia. This is the Danakil Depression we were just talking about, the Red Sea and the Gulf of Aden. And these are the sort of the simplified structural elements in here. There's Mount Kilimanjaro, which is active volcano. Mount Kenya is not. There's a number of volcanoes in here that are quite interesting. It's a natural laboratory for studying how continents break up. So as we said, there's two branches. There's the Western Rift. Sometimes it's called the Alpert Rift. The Eastern Rift, sometimes it's called the Gregory Rift. We won't use those terms though. So East African Rift System in the north begins in Ethiopia, and I think it's arguably the world's most famous rift. It was also the one that got Marie Tharp excited when she saw similar structures in the Mid-Atlantic Ridge. And this is the Kenya Rift. It is the eastern arm of this East African Rift coming down through Lake Turkana. And then this is Lake Victoria. And this is a block about the same size as the Colorado Plateau. Does anybody have an idea why the rift would do this? What this tract of lithosphere might be called? Anybody? It's a craton. So the rift is going around it to avoid, because the cratons, as you know, are relatively cold and strong. So there obviously must be weaker lithosphere on either side that's being exploited, and we know that's true. All right, so here is some example of the northern part of the East African Rift in Ethiopia. So here some people break the African plate into the Nubian plate in the west and the Somali plate in the east. We could argue whether this represents a plate boundary or not. It certainly is an evolving one. Whether or not it's reached the point of being a plate boundary or not is a good topic for argument. But what you're seeing here are discrete segments that can be identified, right? These are magmatic. So there's plenty of structural faulting in here. These are normal faults with the little ticks on the down thrown side, like you're seeing here. And you can see the main architecture of these extensional basins is a master fault on one side where most of the displacement is accommodated, lots of little faults, and then sort of gently asymmetry dipping in one way, and then sometimes igneous rocks coming up. And that's what we're seeing here. We're seeing a number of segments. I guess we could say there's 1, 2, 3, 4, 5, 6 segments. And these are reminiscent of those upwelling cells that we saw beneath the East Pacific Rise and on the Mid-Atlantic Ridge, where the magma supply is concentrated in the middle of the segment and then diminishes to the margins. Plenty of seismic activity associated with these regions, and the extensions, the focal mechanisms show a lot of extension. You can see that there's this extension up here is more northeast, southwest, and down here it's more east-west. So we can zoom in on here. Here we're looking at where the seismicity is concentrated in this segment in here, a lot here, then it's over here, then it's over here. With the focal mechanisms showing consistent extensional focal mechanism, as we would expect. And the depth of the seismicity from northwest to southeast, A to A prime, right here. Lots of earthquakes on the margins. Does anybody have any ideas why there's no earthquakes in the middle? Anybody have any ideas? It's probably too hot to rupture brittling. All right, so here we can see the overall seismicity for the East African Rift, right? The green and red dots, the green triangles are earthquakes, and I'm sorry, the red dots are earthquakes, and the green triangles are volcanoes. Now we can take look at some crustal velocity structure across the Eastern Rift near the equator. So let's go back there. So there's the equator. There's the Eastern Rift. So we're sort of looking in this region. And we're looking at two depths. Here on the left, we're looking down to 200 kilometers. Here on the right, we're only looking down to 50. So this dashed box here is showing you this area. So these are, anybody have an idea of what we're plotting here? Anybody got a guess what these numbers correspond to? You can see on one of them it says km per second, so it's kilometers per second. That's speed. Does anybody think that we're looking at?
P-wave?
P-wave velocities, yes, thank you. These are clearly P-wave velocities, and you'll immediately go, oh, there's 8.1, that's the mantle, 6.8, this is the moho. This line here is the moho, right? This is the crust, upper crust, lower crust, upper mantle. So over here, looking at depth, we see low velocity mantle beneath the rift itself. And then off to the sides, we get back to normal velocities, which the nominal velocity for the upper mantle is 8.1 kilometers per second, like we see here. But right underneath the rift, we don't see that. We see 7.6. Does anybody have an opinion of what that is representing? Why it's lower than 8.1?
This will be a bad guess, but it's sediment fill that isn't as dense, and so the sound wave travels slower.
There's no such thing as a bad guess. That is wrong, because we're down at 20 or 30 kilometers, and the sedimentary basins are nowhere on Earth deeper than 15 kilometers, and they're all going to be up at the surface. This is the sedimentary basins up here. It's not a very big one because this system hasn't been going for very long. No, this is interpreted as a region that is relatively slow because it's hot and or because it's got small amounts of melt in it. And we expect that there's going to be slightly low seismic velocities beneath regions that have active volcanism. those magmas that are making the volcanoes have to come from somewhere. And the natural place for them to come from is partially melted upper mantle. Okay. Does that make sense? All right, so this is tomography, right? We're looking at variations, differences in P wave velocity in percent as as a function of different depths. And you can see that this seismic velocity here beneath the mid-Ethiopian rift or middle Ethiopian rift is relatively low. And here's another one. These are two different sections. And you can see that in all cases, you've got this relatively low velocity upper mantle, presumably because it's got a significant amount of partially molten magma sitting in it. All right, so as we said, narrow rifts occur in areas of slightly higher heat flow than normal, whereas your wider rifts are in regions of much higher heat flow than normal. Now, this is topography, gravity, and crustal thicknesses across the East African Rift. So let's look at crustal thicknesses. Right, so here's the central mid-Ethiopian Rift right there. And what we see is, that's a topographic low, as we'd expect. And we can see that the crustal thickness is just a little bit lower than normal underneath it, as we expect. Now, what's interesting is we see a Bouguer anomaly here that goes from minus 200, the flanks go down to minus 240, and then underneath the axis, it goes up to minus 180. So does anybody have an opinion why we would have this Bouguer gravity high here relative to the margins? That's a tough one. This isn't a geophysics course. But the answer is, what's that?
Is it cooled off and became solid again?
No, it's because the crust is thin and the mantle, which is denser, is rising up. So it's what we're seeing here is kind of surface on the moho. So this is this area which, even though it says minus 110, minus 120, this is a region of broad area of gravity lows and a gravity high sort of in the middle. All right, now one of the interesting things is there's oil here, and this oil was discovered beginning in Sudan in the 1980s, created some unrest in Sudan because in southern Sudan, they had the oil and there was a lot of politics. So there's this entire Cretaceous rift that goes out, can be followed here, that's been drilled. And more recently, people have actually found oil in these very young sediments here, sedimentary basins, next to Lake Albert, which was quite a surprise because the sediments are very young, but there's plenty of biological activity, plenty of organic matter, and high heat flow, which is exactly what you need to make oil. So these systems are quite interesting. It's a huge boon to Uganda. Uganda is not a rich country, so to have access to this resource, all it is can they use it wisely, or is it going to ruin everything like it does so often in other oil-rich countries? We'll see. All right, now let's talk about wide rifts. That, the world's best one is there, the Basin and Range. So here we are, California, Nevada, Utah, Arizona, Oregon, Idaho, Wyoming. We were sort of playing up here with the Snake River Plain and Yellowstone last week. But we're going to talk about this region. So this is a topographic map with lots of earthquakes. And what you can see is the Basin Range itself is not very seismically active, which tells us immediately that it's not tectonically very active, but its margins are. And of the two margins, the western margin of it and the eastern, the western margin is much more seismically active. And this area is very interesting, and we'll talk more about it when we talk about the transform fault in here, right? This is the San Andreas fault coming up here. This is another structure that's very interesting. But then this is the Wasatch Front, which goes right through Salt Lake City. There's seismic hazard there. But most of the Basin and Range is relatively seismically quiet. All right, so here we have the Basin and Range province. This is how we look at sort of the mega structures of the Western United States, the Colorado Plateau, relatively stable block. The Grand Canyon flows through here. You know, Colorado River goes down to Baja, to Gulf of California. This is the Basin Range province, which continues into the Sonoran Desert of southern Arizona and Mexico here. Here we are looking at it, you know, sort of on a geologic map.
And
What's that?
I was going to say, and right, yeah, it wraps around and even has something to do with business in northern Mexico and the Big Bend area where we had volcanism.
Yeah, the Big Bend. So here's the Basin Range province. Here's the Colorado Plateau. Here's the area in Arizona and Mexico, southwestern New Mexico, far west Texas, and the Rio Grande Rift, you know, is sort of shown as a separate thing, but I think you could argue that this entire extensional regime included that. It's just, you know, the Rio Grande Rift, we treat it as something special, but it probably isn't. Its evolution is linked to the extension event that caused this entire feature. All right, so we can use GPS and we can sort of look at velocities. So these are, you're recognizing these as relative plate motions. These are GPS. So this is something like Ravel, kind of a plate model. And what we can see is here's the Pacific plate moving that direction relative to fixed North America. So we're fixing the Colorado Plateau as basically not moving. And we're just looking at, if we do that, then the Pacific plate is moving this direction at 50 millimeters a year. And then we can look at the motions, how this strain is being distributed across this broad margin. So it doesn't go from 0 to 50 across a very sharp line, except maybe down in the south. But in the north, you've got part of the Central Great Basin is moving west relative to stable North America at about 3 millimeters a year. And then much of California is moving to the north, parallel to the Pacific, but at a slower rate. So the strain's being partitioned all across here, and much of that is being picked up by these things. So here's the Intermountain Seismic Belt, which corresponds to what's going on in Utah, which we call the Wasatch Front, right? Relatively small amount of strain. And then this region here we've got the Walker Lane in this vertical striping. Here we've got the Eastern California shear zone in this diagonal striping. And then the Eastern California Central Nevada seismic belt going through here like this. So there's a bunch of different names that are confusing. You don't have to remember them. But the point is that when there's a lot of stuff going on, things get a lot of different names because people are looking at them from different examples. So, you know, this basin and range is 500 to 800 kilometers wide, depending on where you're measuring it. And that central basin range has something like 250 to 300 kilometers of extension since about 16 million years ago. What geologic time period was 16 million years ago?
60 million would be the Triassic, Jurassic.
116.
Oh, 16.
Yes.
That's the Cretaceous.
No, that would be the Miocene. You may want to study that for the midterm. I'm going to make sure there are questions about geologic time on the midterm. So this is Miocene extension, right? Miocene was from about 24 to about 5 million years ago. A very important time in Earth history. All right, and now we can look at the characteristics of wide rifts. The first one is the seismicity. Wide rifts have broadly distributed deformation as reflected by their seismicity. So we can see that the deformation in the Basin Range today is concentrated in the west, but there's a significant amount in the east. There's significant seismic hazard in here. And that's one of the characteristics of wide rifts, is they have very broadly distributed deformation. And here we can see the GPS motions of the Basin Range versus California. So the directions are sort of the way that this material is moving relative to something fixed farther east. The length of these arrows correspond to its velocity, so that an arrow that's that long is 10 millimeters per year, right? Over here in Western California, that's moving northwest at something that looks like about 20 millimeters per year, right? 15. But here in eastern Utah and Nevada, mostly it's moving a little bit west, not very fast. All right, now here's a map of crustal thickness. And we are looking at a colored map showing crustal thickness. We don't see a scale, but it suffices to know that the regions in blue are thicker. Oh, there's contours. So there's 45-kilometer contour thickness for the crust underneath Colorado, mostly. And here in the Northern Basin Range in Utah, it's down to 30. So it's almost half the thickness. And this is coming from these receiver functions. And so here's AA prime, which is this section, and BB prime, which is this section. And so this reflector here is taken as the MOHO. As you see how it's shallower beneath the Basin Range than it is beneath the Rocky Mountains. Okay. All right. Another characteristic of wide rifts is that many of them form on previously thickened crust. So you remember that the Wilson cycle ends with a continental collision and then rifting starts again. And in fact, as we will explore later in this class, regions of thick continental crust are actually weak. So if you want to weaken the crust, the continental crust, the way you do it is to thicken it. And what we see in the Basin Range is this was an area of thickening in the Cretaceous, right? So here we're looking at a map, and we're seeing this is the extent of the Paleozoic passive margin. Now, this is very interesting because normally we think about the West Coast of the United States as being an active margin, either a strike slip fault or a convergent plate margin, like up in Oregon and Washington. But here we're showing it as a passive margin. And that is in fact true. During the Paleozoic, this was the craton. This region didn't really exist as continental crust at that time. And the boundary between the craton and the precursor to the Pacific lay here. This was a passive margin like the Gulf of Mexico or Eastern North America. Now, in the Cretaceous, there was a major orogenic event called the severe orogeny, which was a precursor to the Laramide orogeny, and this was a region of crustal thickening. Okay, so this region was sort of transitional crust underneath the passive margin. Tectonic events shortened it and made it into sort of a mountain range. And that was the situation that existed at the end of the Cretaceous, right? When was the end of the Cretaceous, Wally? Do you know about in millions of years? Are you there?
No, I don't know about that.
It's
Yeah, I'm
65.
here because my video is not coming.
Oh, okay.
Something going like that.
Oh, you're not able to see this?
No, I can pay, but my video is not coming.
Okay. It was about 65 or 66 million years ago. And the end of the Cretaceous is a very useful time for geologists to know. And it wouldn't surprise me if there's a question about that on the midterm. All right. Now, one of the interesting things is a concept called the Nevadaplano. Now, the Nevadaplano is the idea that, so it's sort of a funny word. So the Altiplano is a high region in the sort of central southern Andes in northern Argentina and Chile and places like that. It's elevated. And so people just said, oh, let's call this region that we think existed in the early tertiary, maybe in the Eocene, 30 million years ago, before the Basin and Range formed, as the Nevadaplano. So the idea is that Nevada was an uplifted region, and these arrows are showing you old stream valleys that flowed off of it. And the location of these ancient canyons is well known because they were sites of alluvial gold that were mined extensively during the middle of the 19th century, right? The California gold rush focused originally on these deposits. Okay, so we don't see the source of these rivers today. They're somehow have to be in this region, and so this must have been a higher region than this region in order to provide the water and sediments needed for that. So here you see the way people reconstruct it. So here's in the solid line is the present day topography across Eastern California and into Nevada, across Nevada. And then this is what the topography is thought to have been like during pre-extension time, pre-Miocene time, right? We talked about the Basin Range extension occurring in the Miocene. So this would be something like the Eocene or the Oligocene. And these are a lot of calderas. There's lots of interest in mineralization associated with these calderas, lithium deposits, for example, silver, gold. Yes, Clint.
Yeah. Would this have any connection with the Colin type deposits?
Carlin.
Colin.
The Carlin type gold deposit. No,
Wait, is it Carlin? Okay.
Carlin. Carlin. Yes. Carlin type gold deposits are a big thing in Nevada. Very rich deposits. There's no visible gold. It all has to be treated chemically to extract the gold. But yes, this tectonic situation is associated or maybe responsible for that kind of mineralization. Yes, good point. We'll discuss this probably in the class I teach next fall on ore deposits.
I really want to TA that.
Well, you'll probably get your wish come true, unless you take it. You know. But here in Texas, we have a lot of plastic sediments that may have come from the Nevadaplano. And in East Texas, there's a very important sedimentary horizon called the Wilcox. It's Eocene in age. And you can see here is the Gulf of Mexico going, from onshore to offshore. There's the shoreline. And then this is the Wilcox in the subsurface. The oil companies know this very well. Some of the source rocks are there in the Wilcox. Why do we think the Wilcox was coming from the Nevadaplano? Well, it's because of the uranium lead ages for detrital zircons in it. which have been studied, and we see a tremendous number of ones 78, 90, 170 million years. These ages are unknown from this part of the world, from Texas, Arkansas, Oklahoma. There are no igneous rocks of that age. In order to find source regions that could shed those zircons, we have to go to this region. This region has lots of igneous rocks of that age. So the Nevadaplano and the sediments derived from it even play an important role in the economic geology of Texas. All right, so how do we go from thickened continental crust that existed in the Cretaceous and even into the early Cenozoic into the present Basin and Range? And this is one way that people do it. So here we have a sequence of crustal profiles from a compressed to an extended. And what we're looking at is a bunch of thrust faults, which led to the thickening of the crust to form the Nevadaplano. And then the forces that caused compression are some reason released, and we can talk about what might have released that. And that allows this entire region to relax. This is relaxing. And this region is weak because the crust is thick. It is weak. We'll talk about that later in the course. And it just keeps extending. This LCF is lower crustal flow. This refers to the rheology of the warm lower crust. It's going to flow. And we see here this very interesting style, with these upper faults that are flattening with depth beneath a region that's not faulted. I'm sorry, above a region that's not faulted. And we'll talk more about this. So that's the collapse of the Nevadaplano to form the present Basin and Range. It's a very interesting sequence of events. If we were teaching this course at the University of Nevada in Reno or Las Vegas, we would be talking a whole lot more about this. And maybe we would be teaching an entire course on the geologic evolution of Nevada and its mineral deposits, and that would be fun. All right. Now, another characteristic of wide rifts is that they have thin mantle lithosphere and high heat flow. So here we're looking at the long wavelength Bouguer gravity anomalies, which are indicating where the low density mantle is. That's a asthenosphere. And you can see this region in the Western United States has this broad region of low density. This is low density upper mantle. This is thickened continental crust, and they give you the same effects. So these Bouguer anomalies require some interpretation. Now, we've said that there's high heat flow is characteristic of regions with wide rifts. Here we see a heat flow map. This is a very important product of SMU. Up until a few years ago, SMU had a big geothermal lab led by a very accomplished scientist named Dave Blackwell. He retired. And you can see that we've got very high heat flow in this region. So it's no accident that when people are talking about geothermal energy, they're not talking very much about Texas because we don't have very high heat flow. They're talking about these regions that have very high heat flow in red. Okay, and you can see that here's power plants, geothermal power plants, volcanoes. Volcanoes and high heat flow tend to go together. And then there's lots of volcanic rocks. This is a map of Cenozoic volcanic rocks. Now, it's only the western part of the United States, but it's also the map, with the exception of Hawaii and Alaska, obviously, of Cenozoic volcanic rocks in the United States, period. There's no Cenozoic volcanic rocks east of here. right? So we've got a little bit here in Texas, down in Big Bend country, quite a few in New Mexico, Colorado, Arizona. Yes, Clint.
There is that one little exception way over in Virginia, two little bitty volcanic EOS features from the Eocene, but never mind about them. They're not part of the big picture.
No, and
They're
these
just
are,
weird.
for the most part, these are Neogene, right? The last half of the Cenozoic. Although the Texas volcanics down there in the south, they are Oligocene, and they're older by a little bit. And then up here, you can see Yellowstone. You know, we can't forget Yellowstone and the Snake River Plain and the Columbia River flood basalts, which we talked about last. All right. Now, another thing that we haven't talked about, we've talked about rheology, the strength of existing lithosphere when it's under extension. And we've talked about Byerly's, the brittle strength and the ductile strength and how this is influenced by heat flow. But there's another consideration, and that is if you actually intrude a dike, a basaltic dike, that reduces the strength in this two-dimensional profile to zero, right? This is magma. So there's no strength across that. Now the plate, the rift can have strength because the dike doesn't extend infinitely in the third dimension. But locally, where there is igneous diking, and for the time that diking, that dike is full with liquid magma, it has no strength. It's something to keep in mind. All right, so another characteristic of wide rifts is there's a lot of normal faults. And now there's lots of normal faults in narrow rifts too, but they're much more focused on the rift itself. Whereas in a wide rift, they're going to be distributed across the rift. So here we're looking at kind of an old geomorphology explanation for basin and range topography. And some of you may recall that the basin and range, when viewed from space, if you look down on it, you see these basins and mountain ranges. They're all aligned kind of north-south. And someone once referred to them as looking like an army of caterpillars marching north. Well, this is how they form. So the upper part of the extending region, and we're talking about here is this part, the part you see at the surface, not the deeper part. We'll talk more about the deeper part later. This upper part, with these normal faults, this is what happens, right? You get faulting, you get this displacement, erosion does this, carves canyons, builds alluvial fans, and over time you end up with something like this. Now this configuration never happens because as soon as one piece comes up, another piece goes down, erosion and sedimentation takes off. But it's a useful conceptualization of what's leading to this kind of topography, right? These are mountain ranges with big, broad alluvial fans and playa lakes and things like that. All right, and so there's lots of normal faults, and we can study them at the surface, right? We can go out to the field and walk around and look at them at the surface, but we don't know. We imagine maybe they continue like that to the center of the earth, but they don't. In order to understand what they look like at depth, we have to use geophysics. And so here is some seismic profiles here that have been put together. And here you're looking at the reflectors. This 2-way travel time. That's 10 seconds. Right? So depending on this velocity, that's almost certainly the MOHO, down at 10 seconds. And then you see these reflectors, which are not vertical at all. They're quite low angle. And that's what impressed people in drawing these kinds of profiles is, steep normal faults near the surface that flatten with depth and actually turn into non-faults, just zones of high strain. So we've got both, near the surface, high angle normal faults, and at depth, they're low angle normal faults. Okay.
And, question.
Yes.
Is this what you would call listric faults?
Yes. I think I defined them later. These are, since you raised the issue, these faults, which are steep near the surface and flatten with depth, are listric faults. Right? They become subhorizontal with depth.
Which is named for the French word for shovel.
Is it?
They're shovel shaped.
Le
listron.
Oh.
Le listron with which we bury you.
Yeah. All right. So this gets us back to our strength profiles. So here we've got a typical strength profile for continental crust, right? Strong, shallow, weak depth at depth, depending on temperature. We know that when the MOHO temperature is higher, the strength profile is greatly reduced. But notice that there's very little strength in the lower crust, and we don't get to see that. We get to see its effects when it comes to the surface, but we can't see it happening in real time. Now we need to make a short diversion here to talk about shear. So shear is a kind of strain. So here we're looking at a sort of idealized shape that's being subjected to deformation. It's straining, and we got two different kinds of strain that are being captured here. One, the original axes of the object are being rotated, and the other one they're not, right? There's the original axis, that's Z, that's X. Z and X are both rotated about 45 degrees by this deformation in this example. In this one, they're not. One is lengthening, the other one is shortening, but they're not rotating. So that allows us to distinguish two types of shear. One is called simple shear, where we rotate the axis of the strained ellipsoid. And the other one is pure shear, which is there's no rotation. And if you're like me, you're confused by this terminology because, this to me seems purer than this. This seems simple. This seems pure. That's not the way to think about it. The way to think about it is simply, this looks like a cube. It was cubically compressed, so nothing was rotated. So I can still recognize, if not a cube, at least something that is got right angles. So cube has got a U in it. So this is pure. That's how I remember it. And simple is the other. So some of you may not be as dyslexic as I am, but that's how I remember these differences. All right, so let's ask a question. Logan, is this pure shear or simple shear?
Are you me?
Yes.
Oh, okay. I think it's pure shear.
Does it look like the strain, the principal axes have been rotated?
It's simple shear, and the second one is pure shear.
Yes, because it looks like those fold axes must have been originally vertical. They've been rotated to subhorizontal. This is a good example of simple shear. So this lower one, is that pure shear or simple shear?
I think lower one is pure shear.
Yeah, it looks like it has those axes have not been rotated, right?
Yeah. It just folded a little.
Yeah. So it's useful to have some examples and be able to apply these complicated concepts to real rocks. So yeah, good. All right, now we can you apply these concepts to our discussion about what happens during extension. So we can imagine an extending lithosphere, and we can imagine it being subjected, responding via pure shear, or we can imagine it responding via simple shear. And here we have two very simple examples. In both of them, it's only the upper part of the lithosphere that's showing these faults that are so spectacularly preserved in the Basin and Range, these vertical, near vertical faults. And then at greater depth, we've got some kind of ductile flow. This ductile flow is consistent with this strength profile, right? This region is very weak and it's going to flow easily. That's what we're seeing here, right? But in this case, everything is being sort of symmetrically thinned, from the axis of the extension to the margins, it looks pretty symmetrical, right? So that would be pure shear. On the other hand, we could say, no, what we have is a single master structure that's a fault when it's shallow and then turns into a very focused shear zone at depth that's dipping. And so this system is asymmetric. The crust on one side is thinned more than the crust on the other. And the lithosphere on one side is being thinned more than on the other. It's asymmetric, right? And here we see these faults are listric. Down here, these are all listric faults. Even this is a listric fault. These are steep faults, right? And in fact, the axis where the thinning is greatest here is right under the axis of the extension. Over here, it's offset. So even though here the crust is not thinned, the actual lithosphere is most thinned underneath there. All right. So those concepts make sense. And the next question would be, which one is right? And the answer is, there are good arguments about this in the literature. It's important to be aware of the controversy. It's important to be able to apply some of the concepts that we've developed about rheology to our understanding of rifts. But I would not venture to say which one of these is generally most appropriate. Does the lithospheric structure beneath the basin and range look like this or like this? That is a very deep and interesting literature to examine. Both sides have been presented. All right, now let's talk about core complexes, which is kind of put up here as sort of the next step beyond wide rift mode. So core complex is a very wide rift, and its formation implies very high heat flow and very weak lithosphere. This is kind of a really exciting example. So now if we say that this gray area is the area that's being extended, right? The area of the lithosphere. So this gray area is lithosphere that's being extended. Here in the narrow rift, it's focused. Here in the wide rift, it's all of it. Here, there's actually no strength whatsoever in the mantle. All of the strength is, and there's very little of it, is in the upper crust. So this entire system is flowing at depth. All right, what is a metamorphic core complex? So here we have a map showing the metamorphic core complexes of the Western United States in black. There's one there in Mexico, quite a few in Arizona. That's where it was figured out. Here in Nevada, and Idaho, and up into British Columbia. And this is a sort of a three-dimensional, excellent representation of a metamorphic core complex. And what you're seeing here is this listric fault that's high angle, but has actually been exhumed. This fault, which was originally at depth, is come to the surface where geologists can study it. Okay? Shall we watch a 7-minute video?
In Arizona, when we think of geology, we immediately think of the spectacular sedimentary rocks of the Grand Canyon. Yet, hidden beneath the desert landscape of Saguaro National Park, the metamorphic rocks of the Rincon Mountains tell a story that is no less wondrous and much more complex. These metamorphic rocks have risen to the surface of the Earth from deep inside the crust, where intense heat and pressure transformed them into something entirely different than sedimentary or volcanic rocks. In Saguaro National Park, they were exposed in what geologists around the world recognize as one of the most stunning examples of what they call a metamorphic core complex.
Classically, we think of mountain systems as having formed through compression, shortening, thickening of the crust, and uplift of the system. Metamorphic core complexes, on the other hand, form through stretching, extension, lengthening of the crust under the influence of tectonic stresses.
For decades, geoscientists from all over the world have come to Saguaro to study metamorphic rocks. But what exactly is a metamorphic core complex, and how did it come to be? To begin, let's follow the journey of a single crystal collected from Javelina rocks, an important stop along the Cactus Loop Drive. This small flake of zircon is thinner than a sheet of paper, yet has managed to survive intact for more than 1 billion years since its formation. Armed with microscopes, tweezers, and advanced lasers, scientists are slowly learning the story of the mountain through these crystals. The zircon crystals that occur at the Earth's surface today are in some ways like microscopic time capsules. By studying the rings in our small crystal, we know that it crystallized more than 1.7 billion years ago, when the earliest life forms were appearing on Earth. Around 30 million years ago, the crystal and the rocks surrounding it began creeping upwards from deep in Earth's crust. By 20 million years ago, it was 4 to 5 miles from the planet's surface. Today, our crystal from Javelina rocks has traveled upwards by more than 10 miles. By comparison, the Grand Canyon is only around 1 mile deep at its deepest point. But how did the zircon crystal at Javelina rocks get to where they are today? The answer lies in the Catalina Detachment Fault, a rare geological structure, largely hidden, that snakes its way through Saguaro National Park. On one side of this fault are shallow, sedimentary, and volcanic rocks that were originally deposited on the Earth's surface, like the rock layers of the Grand Canyon. On the other side are the deeper, crystalline, metamorphic rocks of the core complex. We can think of the detachment fault as a huge crack cutting through the outer shell of the planet. As the metamorphic rocks of the core complex moved up along the crack, the sedimentary and volcanic rocks of the upper plate above them moved down and away towards the west. Eventually, the metamorphic rocks reached the surface in the park's eastern Rincon Mountain district, while the upper plate rocks, which started in the east, came to rest miles to the west in what is now the park's Tucson Mountain district.
Normally, like in the Grand Canyon region, you need a canyon to go deep enough to expose the deep rocks. In the core complexes, the natural process of shearing and faulting as the crust extends brings to the surface rocks that were once buried at depths of 10 to 20 miles beneath the surface of the Earth.
Earthquake by earthquake, over millions of years, the core complex rose up to where we see it today. At the surface, this movement left behind a landscape of telltale traces. Tremendous stretching and sliding along the detachment fault warped the Earth's surface, shaping the park's landscape into a series of undulating waves. You can see this in the Tanque Verde Ridge, one of the crests of these waves. And you can also see it in the W shape of the detachment fault traced along the surface of the land. The fault movement left-lined or linear features that are so consistent in their direction that you can see them everywhere, at the scale of mountains, in the ridges and valleys, down to the scale of individual minerals.
Every single rock is imprinted by this line of shearing. We see it here. We see it here in this sample. We see it here.
In these metamorphic rocks, you can see how the individual mineral crystals in the rocks were stretched and deformed when they were still hot enough to flow while being solid at the same time, like currents in a creeping glacier, frozen in time. These imprints and lines are what geologists from all over the world come to Saguaro National Park to see today. The Metamorphic Core Complex is a place of mystery and paradoxes, and research continues to this day. So the next time you hike among the saguaros in the park, over the hills of intricately layered rocks, take a moment to look closely at them. They have a unique beauty, especially in the evening sunset, but they are also windows into Earth's past, clues from unseen depths of the slowly churning planet below us, a frozen record of our dynamic world.